repeat this part a little bit. We're talking about the issue of the component effectiveness of the HDH desalination systems. And I was given an example of one of the components like the dehumidifier, where basically what enters is water at lower temperature, and then the water temperature increases. I'm following here the dotted red line. As you see, the temperature increases inside the dehumidifier until it leaves at state number 1. It enters at 0, and then it leaves at state number 1. And then the air enters at air 2 at a higher temperature, and then it drops down until it leaves at air 1. Why the air is following a line which is not straight? Because this is basically humid air. We are following the humid air path. It's only the temperature decreases, but we are maintaining saturated conditions for the air. And that's why it's not a linear one. Whereas for the water, sensible heating for the water, it is occurring linearly. So the water heats from 0 down here up to 1 up here, whereas the air cools down from air 2 right here, and then it will keep cooling down until air 1 at the inlet. So this is a condition at the inlet or down at the dehumidifier, and this is the upper point of the dehumidifier. Then we'll say that the ideal case becomes if this water is heated to the maximum possible temperature, which is temperature of the air inlet. So that this difference here is what we refer to as the enthalpy pinch at the high temperature side of the dehumidifier. Whereas the air enters at high temperature, it will condense, it will cool down because of the interaction with the cold water inside the tubes. Air is going to cool down, but it will maintain its saturation condition until it leaves here. The condition is best if the air is further cooled down to the inlet water temperature. And that is the small, again, another enthalpy pinch at the inlet condition. What we do, we compare with this enthalpy pinch and this enthalpy pinch, and the smaller one of them is what we consider in estimating the effectiveness of the unit. For the dehumidifier, things are clear and straightforward because the smallest enthalpy pinches are found at the terminals, at the inlet, here, small enthalpy pinch, and then the enthalpy pinch increases difference between enthalpy of the two streams, keeps on increasing until a maximum value, and then decreases until it reaches another small or minimum value at the end. So when I'm looking at enthalpy at the inlet of the air or of the water, enthalpy at the exit of the air of the water, then fine, that is actually approaching these differences being smaller. It means that the unit is more effective. In the humidifier, the situation is different. Now, the air here has been cooled down in the dehumidifier from state number 2, A2, down to state number 1. In a closed air cycle, it will enter to the humidifier at state A1. It will be heated up again with water sprayed. So it's going to follow the same saturated path, heating up until it leaves the humidifier at this condition. We assume that between the exit of the humidifier and inlet of the dehumidifier, there's no energy loss for the air. The tubes are well insulated. So inside the humidifier, it's a heating process which is going to follow this path. It will be heated by what? It will be heated by the water. So I have water at maximum temperature after the heater being sprayed inside the humidifier, and it will lose its energy to the air, and accordingly it will keep on cooling down. This is water, sensible cooling, so it's linear until the end of the humidifier, point 3. Look at the differences between the enthalpies. At point 3 here, the value of the enthalpy difference at the exit is big. The enthalpy difference here is almost too large because this line is having a smaller increase in the value or the trend. The slope is decreasing, which means that you may or may not have a line connecting between point 2 horizontally to point A2. So in the humidifier, where is the point of the enthalpy pinch, the minimum enthalpy pinch? It is this in the middle. So if the expression that we are using for writing the effectiveness of the humidifier needs to be corrected. For the dehumidifier, there's no problem because the terminal values are the values that are having a better performance. Or in other words, if I come here to talk about the component, which is the, let me insert here a text box. Let me see if I can add it here without affecting the system. Oh, no, this is not what I wanted. I wanted to keep the figure in the same location as it is without affecting it. So it seems that I lost or I missed the graph that I wanted to be there. Sorry. Yes, here we are. So when we are talking about the dehumidifier effectiveness and saying that it is Hn for the air, so it's this H minus H out for the air divided by Hn for the air minus the exit H if it is brought to saturation temperature with the water. So it will be this value. So as if we are looking for difference between A2 and A1 divided by A2 and A1 dash. Or for the water side, it will be H1 minus H0 divided by H1 dash minus H0. So this is something that you can see, and the differences are not large. So having that smallest enthalpy pinch values are evaluated actually at the ends because the differences of enthalpies between the two streams at the end are the smallest. This is the opposite in the humidifier. This is the water which is sprayed in the humidifier, that green dotted line or dashed line, whereas the blue line represents the air heating. The difference in the enthalpy, it reaches a minimum value somewhere inside, it's not at the terminals. So the expressions that we used to write for humidifier effectiveness is not really accurate in that sense. And we need to come up with another expression. Actually, we have been, for a few years, we have been after this issue, and probably you have seen some of our earlier work who are showing performance of the unit with dotted line that shows a violation of the second law of thermodynamics. The violation here is coming because we were not using an accurate expression for the effectiveness of the humidifier, and accordingly, the values that were given was not true because we know the effectiveness, it's talking about a certain difference divided by a maximum difference, so it should be a fraction. And then we extended that work and we kept the same idea that we should satisfy the first law of thermodynamics and second law of thermodynamics and avoid the points of having negative entropy generation, which doesn't make sense, physically and so on, until we came up with this kind of expression. It's not a straightforward when you are doing it in the analysis. Because when you are solving or analyzing for the humidifier, you don't know exactly at which point this kind of local minimum is going to be achieved. Actually, when we are looking at the effectiveness of the humidifier, I would say that it is HA2 minus HA1 divided by HA2 minus HA1 plus psi. Psi here is the enthalpy pinch of the humidifier. So that's a new definition here for the effectiveness of the humidifier. And this definition, if we need to apply it when we are analyzing problems, then we need to identify where is this point. So we have one of two things, either to keep on measuring the temperature difference between the air stream and the water stream at every location in the humidifier until we reach for the minimum one, Or alternatively, we can look at the slope of the water line here. Water is being cooled down, it is sprayed hot at 2, and then it will lose heat that will be gained by the air, and the heat is going to be lost until it leaves the unit at 3. So this is the line or the slope of decreasing temperature for the humidifier. Then we try to match tangent lines of this line until they are parallel. When they are parallel, it means that we have reached for the condition of minimum entropy or minimum enthalpy pinch, which is corresponding to minimum entropy generation. And that's the ideal case, or this is the case of highest effectiveness. Here on the figure, things look persuading, they look nice. But when you are doing this in a program, it means that you need to break down your humidifier into several parts. And in each part, you're trying to come up with what is the air temperature, what is the water temperature, what is the difference between them. Or you can even look at it or search for it by the slope, that this line and that line have the same slope. And this is the location where you can calculate your difference in the enthalpy between water and air as your minimum or enthalpy pinch of the humidifier. There's a lot of work behind that. I just wanted to show you how the picture would be looking like. Now, we said here that this is a condition where the system is said to be unbalanced, which means that there's a deviation between the values of the enthalpy at the terminals between the hot water and the humid air. What if we try to minimize these differences? So the idea of thermodynamic balancing come here, that instead of making our humidifier a single unit, we're going to make the humidifier at 2 units. Actually, they are not 2 units, but simply we come at the middle of the humidifier and we make a connection from humidifier to dehumidifier. As if you have broken your humidifier into 2 pieces, your dehumidifier into 2 pieces, and the 2 pieces are connected in series. So air is going to enter at the first humidifier, it will be heated a little bit, and then it will leave the first humidifier to enter the second humidifier where it will continue heating. Water enters the humidifier at high temperature, it will cool down to this temperature where it will leave it and enter to another humidifier where the slope is going to change. And the same thing applies for the dehumidifier. Look at this figure compared to the previous one and look at the minimum enthalpy pinch. It is much smaller, which means that it is more efficient. If the effectiveness is higher, then the whole performance is better. The productivity is higher and the GOR is higher. And this is what we are looking for. So the idea of having a balanced system thermodynamically, which means that we have made a connection between the humidifier and the dehumidifier somewhere in the middle, or simply we have divided the humidifier into 2 parts, the dehumidifier into 2 parts, and we made a connection in the middle. Or you may have a system with 2 extractions, and the results are shown here. So if this is first part of the humidifier, second part of the humidifier, third part of the humidifier, you can see here the enthalpy pinch is almost 0, so it's an ideal condition. Here it's too small, here it's too small. So talking about the overall effectiveness of this unit is higher, and that is going to lead to higher GOR. There is a paper which has the whole details of this work there, and it has an example. The example is taken the case of no extraction, no unbalanced system, and a system with a single extraction, which is a system of breaking the humidifier and the dehumidifier into 2, and a double extraction where we are breaking it into 3 pieces. And for the conditions, we are looking at how much the productivity and the GOR of the system has changed. You will see that this values in the paper, that going from this system, a GOR of about 3, to this system, a GOR of about 5 or so, to this system, to a GOR about almost equal to 8, which means that thermodynamic balancing has resulted in a significant increase in the performance parameters of that HDH system according to this value. This work is recent, and actually this is something that we have learned over the years, and the results have been compiled in a paper that appeared in Energy Conversion Management last year. The paper actually is a little bit long, so that's why we broke it into a paper and supplementary material. So I put the paper and the supplementary material, both of them in the Blackboard so that you can see them. I uploaded, I mean, we have lots, tens of papers related to the HDH system. So I just selected this one. I selected the work I represented last time, which is the optimum design of an HDH system, which was one step before we consider this, the one that you see in front of you. However, the paper that you are going to see, which is in Energy Conversion Management, which is in the Blackboard, it will give you a procedure to follow in case of you want to solve a problem with zero extraction, or with a single extraction, with a double extraction, and it will guide you into tables and figures where you can extract values and then come up with a solution. So it is the similar idea that we did in the 2014 paper that I discussed last time, that you may need to get back to figures, you may need to get back to tables so that you can get your outputs, and without having to do much calculations, you can design a system for the productivity that you want. So that paper that appeared last year that I put today is some sort of an update to that information, which is expected to be a bit more accurate. So I'm leaving that paper for you to read, and then we probably will change the subject now, but we may get revisited back if if you need to bring this issue up again. And even we can invite one of our graduate students who was basically doing the details of that work so that he can speak a little bit about the work that they have done and how they come up with these tables and values. What we need to get into today as another technology for desalination is what we refer to as the membrane distillation systems. The membrane distillation system is an emerging solar desalination, which is, a thermal desalination system, which is having a combination of a thermal system as well as we are still using membranes. This technology have been used, it has been there in the industry for decades, but it was not used for water desalination. It has always been used in juice extraction factories as well as in pharmaceutical applications. But it started coming into the desalination technology not too far. Maybe they started talking about in the 90s, but it was not until maybe 2010 where the work related to the membrane distillation has started to increase tremendously, and people showed great interest of that technology. We have a presentation. We started the work with membrane distillation in the university by Dr. Ataya Khalifa and myself, who just started it, and then we started every time we are learning something new as we are doing models or as we are building experimental setups for that. Again, we are coming from the same origin, talking about the water energy nexus, the issue of water shortage, the need to desalinate the water with the smallest energy consumption possible is basically our target. This is the objective, what we are looking for. We need to get as much water as we can to be purified with as less power or energy spent as possible so that the system becomes effective. And this is behind what is called the energy-water nexus. The need for water and the need for energy keeps on increasing due to the increase in population, human activities, industrialization. We started looking at alternative energy sources because we're looking for something which is non-depletable, sustainable, and something which is always there. It's does not have carbon footprint on the surroundings, and it is reliable at the same time. Solar, wind, geothermal, nuclear. These are examples of sustainable systems. Solar is the origin because the solar energy is the origin for the wind energy. Just geothermal needs a very long life cycle because some places under the earth crust are at very high conditions of temperatures and pressure. So at locations where the crust is weak, you can find that hot water or steam is emerging from the ground. This, I mean, the geothermal plants are many in the world actually. Italy is very well known to have geothermal plants. There is a potential of geothermal energy in the kingdom. So far, it's a limited potential, but discoveries are still on, looking for further locations, because in this condition you are getting freely hot water or steam sometimes, which is coming from the ground, and then you can use it for whatever application that you want. It is not pure water, it's having lots of minerals, and that's why, again, in some cases, they take this water, pass it into a heat exchanger to generate steam, and the steam operates a power plant, and then you have power. This is about the water scarcity. That's something that we have seen before in the introduction to the course. And here we are just pinpointing the points or the locations that are suffering from scarcity of water. And the dark color here is an indication to locations in the world where there is water poverty, natural water poverty. The same thing applies here in the lower figure, which is talking about the water stress and expected to be more and more with time. So issues here that it's going to touch much more of the population on Earth is an issue. We're expecting by 2030 to have half of the world population are living in areas of high water stress. So we're considering shortage of water accordingly. This figure, again, it's a 2009 figure. The values definitely has changed, but the trend is kept. Saudi Arabia is still the highest producer of desalinated water, followed by the United States, followed by United Arab Emirates, and so on. And for a desalination process, basically, whatever the desalination technology it is, you have saline water coming in, which is either brackish or seawater. You have energy coming in, and the product is going to be brine and fresh water. This is example of thermal desalination systems. Here we see a power plant with 1, 2, 3, 4, 5 5 boilers actually. And the 5 boilers are feeding 5 steam turbines, and the steam turbines are connected to generators to produce electricity, but we are extracting a line of steam from one of these turbines to operate a desalination unit. Examples here for the thermal desalination systems is multi-stage flash desalination, multi-effect desalination. Both of them can be operated with a vapor compression unit. We'll be talking about each one of these components in details, writing the models for them, and then seeing how they operate. And for thermal desalination, as usual, what do we have? We have basically heating, evaporation, and condensation. That's the whole process which is happening. It is imitating the natural water or the natural rain cycle in the earth. On the other hand, there is desalination, which is operated by power. We have a salty water in one end, fresh water on the other end. If we left it like this for some time, what will happen? Fresh water have higher chemical potential compared to the salty water. So what will happen is that the sweet water will pass by the semi-permeable membrane to the salty water, and after some time you'll find that this level is going down and this level is going up. But we don't want that. We want the opposite to occur. So what's keeping this kind of continuous motion is the effect of the osmosis effect of the two streams, the two solutions. So we have to apply a pressure which is higher than the osmotic pressure in accordance for the sweet water molecules to leave through the membranes and go to the other side, and then you can collect fresh water. Or from the other, or just in other words, you can convert part of the salty water into fresh water by passing pure water, almost pure water in, leaving the salty water or the high concentration behind. What we have here in the front, in the left side, is basically a combination of cartridges. And each one of these cartridges, it depends on the size. You have 6 to 8 membrane units, and these are basically the modular sort of arrangement for the RO system. What are we looking for? Alternative technologies. We are looking again, as I mentioned earlier, that we are looking for the maximum amount of water that we can extract and the minimum amount of energy that we can put in. And we need low cost, we need no pollution, and we're looking for national security, that to have water which is enough for the population. Several technologies are there. The one that we are picking up to start talking about is the membrane distillation technology. In the membrane distillation technology, it is basically a thermally driven process. So although there's a membrane there, but the process is thermal. Why thermal? Because in one end we have high temperature, on the other end we have low temperature. High temperature means higher vapor pressure. Low temperature means lower vapor pressure. So the difference in temperature creates a difference in vapor pressure, and the difference in vapor pressure moves the particles of the vapor from the high temperature to the low temperature side. So this is what happens here. You have a hot field, you are heating seawater up to a temperature somewhere between 50 to 90 degrees centigrade. So again, we are talking about low grade energy here. Relatively warm temperature, 50 to 90 degrees, is passing here across a membrane. The membrane is hydrophobic. Hydrophobic means what? Means it allows the vapor to pass, but it does not allow the liquid to pass. So water vapor is going to pass through the membranes. The other side, we condense that water vapor and we collect sweet water. That's the simple idea. You create vapor, pass the vapor by the membrane is going to absorb, or it's going actually to allow for the water molecules to pass, for the vapor molecules to pass, because this is what we call a hydrophobic membrane that allows vapor to pass. It does not allow water to go through. And then the vapor will go to the other side where we condense it. And it depends on how you condense the vapor to have a classification of the membrane distillation unit. So membrane distillation unit, it has membranes, but it is a thermally driven. It's a thermal desalination system, because the major changes here is, or the motive here is the change of vapor pressure, which is coming as a result of a decrease in temperature. So the vapor pressure is the one that creates this flow from high vapor pressure to low vapor pressure side across the membrane. So the molecules here, we have water molecules and salt molecules. The vapor molecules are the ones that are able to pass through this. The process has been known since 1963, but it has not been into the desalination industry until lately. What are the benefits of membrane distillation system? Temperature is low, relatively speaking. We're talking about temperatures that starting from 50. So 50, 60, 70, this is good enough for membrane distillation process to start. We can use accordingly, since we are only heating to temperatures that are in the order of maybe 70, 80, 90 degrees. So we can think of low grade or low grade energy or low quality energy like waste heat. And that's something that we have did before, talking about, maybe I mentioned to you that we were using in one of the experiments the heat of the exhaust of the car to heat the seawater and run a membrane distillation system. Solar energy definitely is something that we have tried earlier. We have done or we have built solar units that are desalinating the water through this technology, membrane distillation. You can use energy rejected from a condenser of an air conditioning system, anything that has low-grade energy rejected, then it's good enough to operate this unit membrane distillation on. So there are a few things that we have tried with that. One of the things that we're thinking of lately, and even we had we've been presenting in the previous semester in one of the conferences, talking about membrane distillation system, which is operated by the heat rejected from a heat pump or a vapor compression system. An air conditioning system, the condenser is rejecting heat. We are taking this heat to heat the water, and then hot water is going to pass by the feed side of the membrane, and then it will evaporate. You take the vapor, condense it, and you have sweet water there. So any low-grade energy source that's going to bring us with a temperature between 50 to 70 degrees centigrade is a system that we are going to consider. YMD, again, low-grade energy is needed. You can use waste heat. You do not need to apply high pressure. In the reverse osmosis system, in order to overcome the osmotic pressure, you have to pay a lot. You have to have a pressure in the order of 60 to 70 bars. 60 to 70, the atmospheric pressure. You need to reach for that. And you need to create your membrane to withstand this high pressure. But for the membrane distillation, no, you're in the hot side, you are just passing hot water parallel to the membrane. It does not penetrate the membrane. So you are not pushing water molecules inside pores. Actually, the pores are going to allow the vapor to move. Whatever the quality of water that comes in, the results are very pure. So it is evaporation. So in the RO systems, we used to have the product at a certain salinity, which is in the order of a few hundreds. But here, it's basically zero because it's evaporated and condensed vapor. So pressure needed is not too high. It's not high, it's basically atmospheric pressure, just a pump to drive the hot water through. We do not care about the quality of the water which is passing, just like the HDH system. You are not having any metallic parts that you are worried about corrosion for these units. No, that's not the case. You can make your system all out of plastics, and then you don't worry about the issue of scaling or so. Productivity is good, and it is compact in design. And that's another benefit from using a unit like that. We are talking about basically membranes, and the membranes can be arranged in a flat sheet shape or in a spiral wound shape. Or so you are talking about a compact design for the unit. The classification of the membrane distillation is found in this slide. And I have to bring your attention to something which is important. That is, the feed side is the same for the four subfigures that we have. The shaded thing in the middle is the membrane. The left side of the membrane have hot seawater. The right side of the membrane has cold distillate. Seawater is hot. Say it's close to boiling temperature, something above 90. Whereas on the other side, on the right side of the membrane, you have low temperature. This low temperature, either you are circulating water, and this is what you see here in the one upper here to the left. We call it DMCD. The DMCD stands for direct contact membrane distillation, which is this. So it's direct contact membrane distillation. What is that? Hot water enters here. It will pass parallel to the membrane. vapor will form, the vapor is going to cross the membrane. When it crosses the membrane, it comes here to find circulating sweet water. So here we have water which is passing. Not only water, it is actually sweet water. So what will happen? The water vapor is going to condense in the pure water, and then the amount of water here is going to increase. The increase of the water is the productivity. So this is the simplest direct contact membrane distillation technique. Condensation of the vapor happens in the pure water stream, which is passing on the cold side of the membrane surface. We refer to that as direct contact. From the other side, the second kind of arrangement is this, and the AG stands for air gap membrane distillation. Left-hand side is the same. We have hot water passing here, and we have the membranes. From the right side of the membrane, there is a compartment with only air in. And there is a cold surface here, which is cooled by cooling water. So the cooling water here has a target of maintaining this surface cold, so that condensation of the vapor occurs on the surface. There's another good feature here in the air gap membrane distillation is that this water can be of any quality. Actually, I can bring seawater here as cooling water, and then as the vapor condenses here, heat will transfer to the cooling water. Its temperature is going to increase a little bit, and then you are going to take this here. If you are heating it enough, otherwise you are going to need a heater here. So sort of energy recovery can be achieved here. Whereas here it's got to be sweet water which is passing in because it is mixed with vapor which is leaving here. But here you don't have to. The third one, or the third category, is what we refer to as SG membrane distillation, and SG here stands for sweeping gas. So sweeping gas membrane distillation, basically left-hand side is the same, no change. Hot water passes through a surface of the membrane. So vapor will form, and the vapor is allowed to pass by the membrane pores, because we are talking about hydrophobic membranes, until it passes to the other side of the membrane, where you'll find that there is a gas rotating here in a closed cycle. The gas is taking the vapor from here to an external condenser. So the condensation and production of the distillate water here is occurring outside the units. It's a distillate unit for water collection, basically, or then we wanted to create some sort of an additional motive here for the flow of the vapor to occur across the membrane. And this is what you have seen here in this. The V here stands for vacuum. And I have to tell you that membrane distillation technology is rather, for desalination, is rather new. So there is no existing units that are being sold for producing water. The units which are available and being sold basically are pilot units for testing, or some small scale units for operation for some sort of remote communities, but there's no much companies that are producing this. The technology which is having higher productivity is this, which is basically talking about VMD, vacuum membrane distillation, in a way that you are making vacuum here. The vacuum can be created either using a vacuum pump or by using an ejector, or there are different technologies for creating vacuum here. High temperature, low temperature, high vapor pressure, low vapor pressure, in addition to a vacuum. So vacuum here is sucking up the water vapor across the pores, and then it reduces or actually what happens is that it brings the water vapor here, and then more and more vapor is going to pass through the vacuum, and then it is going to suck out outside the unit where there is a condenser there that will condense the vapor into a liquid, and then you have your product. Is that all about membrane distillation classification? The answer is no. There's another classification that appeared within the last few years, which is what's called as the water gap membrane distillation. It is very much like the air gap membrane distillation system that you see here. But what happens is that you are going to close this gap here. What will happen? You are going to start having hot water passing here, vapor will form, and the vapor is going to cross the membrane, the pores of the membrane, and then it is going to condense here in that place where you have air at low temperature, relatively low temperature, in a small compartment, so air does not rotate. And basically, that stagnant air, which is a layer of, as if a layer of insulation, and then water will start condensing on the surface here. We have closed it from the bottom, so water is going to condensate, and it will until it fills the whole container here. Then, when it is filled, it's called the water gap. So the water gap can eventually be made by starting with an air gap system, but closing the passage of the air and just allowing the water to condense and pile up here until it's filled with water. Then these tubes are in touch with water, and then the condensation and cooling process becomes more effective. So we have direct contact membrane distillation, air gap membrane distillation, water gap membrane distillation, sweeping gap membrane distillation, and vacuum membrane distillation. Any questions so far up to this moment?
In the case of the sweeping gas membrane distillation, is there no risk of contamination? You are using, the sweeping gas to push the vapor. How is it done?
Nothing can prevent it except if you have to eat it. You can say the same thing about the HDH system, because air is passing, air carries the water vapor from a location and transfers it to another location. The sweeping gas, the gas is going to be air because this is the cheapest and most abundantly available gas that can be used. So basically it's air which is passing in, say, a closed cycle that takes the vapor from here, it condenses it in a location, and then it's returned back again to carry another amount of vapor. So it's going in a closed loop sort of thing. So when we're talking about a sweeping gas membrane distillation, basically we mean air, which is being recirculated here so that it takes vapor from here, condense it, and come and take another portion of vapor and condense it, and so on.
Okay.
This is another layout of the system. And there are some spin-off companies that came out of working with pilot units of membrane distillation. In Europe, there is a company called Sakara, which is working with membrane distillation. And lately in Singapore, a new company, which is called Memsift, has started. And the Memsift, the good thing about them is that they are making lab units that you can bring, you can put it to the lab and you can test it. And I just tested most of these units that are having sort of good productivity of the water are basically considering a vacuum pump in the unit, which is always there. It means that they're operating at low pressure from the permeate side. Now for the terminology, the feed side is the supply side. This is where the hot water comes in. So it's called heat side or supply side, or the feed side. And then the other side is the permeate side. So we have permeate in or permeate out. We have cooling fluid in or cooling fluid out. So it depends on what you call it, but it's basically the permeate side where permeation of the vapor is going to go through the membrane where it will condense there into sweet water. Characteristics of the membranes, they are basically hydrophobic membranes. They are microporous, very small pores that would allow the water vapor molecules to pass in. The materials that are basically used for this are polytetrafluoroethyl or ethylene material, PTFE. This is what we commercially refer to it as Teflon. So materials of the membranes are basically Teflon. Polypropylene is another option, or polyvinylidene or polyvinylidene, fluoride, PVDF, and other similar sort of polymers. So the kind of polymers that you are going to deal with, whatever we have in the university here basically is PTFE, which is typically sort of Teflon kind of material. The membrane has to be hydrophobic, and the word hydrophobic means that it hates the water. It only allows the vapor to pass. On the contrary, we can have a membrane which is hydrophilic. They call it a water lover, that only passes the water through it, but it does not pass the vapor. So the words hydrophobic and hydrophilic or philic are words that you are going to use a lot. And again, hydrophilic is a water lover. It allows the water to pass through the membrane pores. And this is basically what we use for reverse osmosis systems. However, for membrane distillation, the kind of membrane we are using here is hydrophobic membrane that does not allow the water droplets to pass. It only allows the water vapor. Can we have a surface that does not allow the water droplets to penetrate through? Yes. All the waterproof surfaces are like that. Any raincoat that you are buying to wear is basically have an outer surface which is hydrophobic because it's a raincoat, then the water or the rain does not penetrate through it, but it just rolls outside, which means that the contact angle between the droplets of the water and the surface is too high, so the surface does not stick to the clothes. It does not penetrate through, it just slides on its surface. The membrane should resist chemicals. It should be stable in the temperature range that we are using in. We are writing extreme temperature, but actually membrane distillation is not extreme. The extreme in the membrane distillation could be something like 90 degrees or so, but normally it is somewhere between 70 to 80 degrees centigrade. For a membrane to be better, it has to be less resistant to mass transfer. It has high resistance to heat transfer. So this is basically the kind of characteristics that should be there in the membrane. The figure here, or the slides, I brought it here just to show you the difference between hydrophobic and hydrophilic kind of surfaces. The one to the right is a hydrophobic one where the contact angle between the droplet and the table is somewhere greater than 90 degrees centigrade, whereas the hydrophilic one is having a contact angle less than 90. The more the hydrophobicity, the better it would be. So having higher and higher contact angles, it means that it's something that we are looking for this kind of application. What we see here is a membrane and its supporting layer. The membrane normally is too thin. It cannot withstand the pressures. So normally we bring a porous supporting layer and we stick it to the membrane so that it can resist pressure differences across the membrane, and the membrane will not be ruptured or broken. Membrane thickness is a characteristic of the membrane. Thicker membranes have thermal insulation, but they have bad mass transfer. Thinner membranes have good mass transfer characteristics, but they lose heat, which means that some sort of a trade-off is got to be used. Ideal membrane thickness has been found to be between values of 30 to 60 micrometers. The pore size is another important characteristic of the membrane. The pore size is somewhere between 100 nanometer up to 1 micrometer, and normally the membranes are characterized by some sort of an average pore size. So membrane thickness is one parameter, membrane pore size is another parameter. There's something also that we call the porosity. Porosity is a ratio between the total area of the membrane or the gross area of the membrane in the denominator, and what we have in the numerator is the areas of the holes or the pores on top of it. Higher porosity, it means that it can allow more vapor or more water to pass, depending on whether it is hydrophilic or hydrophobic. The liquid entry pressure is another issue, which means that what is the pressure of the feed that should come into the membrane distillation unit without affecting the membrane. Most of the membranes have two layers, one active layer and one support layer. The support layer is the layer that protects the membrane from rupture. I think I used to have a figure that shows, the active layer and the support layer. Active layer is extremely thin compared to the support layer. The flux is an expression that we use to say or to express how much kilograms or liters have passed per meter square. The output of the membrane distillation is usually measured in flux. We usually have small surface areas, so that's why the productivity is on the low side unless you are using either spiral wound membranes or large surface areas in general. Then the productivity would become significant. The key parameters that affect the performance of the membrane distillation systems is 4 parameters. We're talking about a thermal desalination system. So temperature is one of them. The feed side or the high temperature side, the hotter, the higher the temperature, the more vapor it would have, and accordingly, it would produce more. So hot side or feed side temperature is the most influential parameter that affects the performance. The cold side, where the condensation is occur, the lower the temperature, the better the performance. Flow rate of the hot side, the hot feed, is another parameter, because higher flow rate, it means higher turbulence, so higher heat and mass transfer coefficients. So the situation becomes better in terms of evaporation. Flow rate in the cold side is another, because again, you are talking about higher flow rate, higher turbulence, and then a higher heat and mass transfer coefficients. When we are talking about membrane operating between 50 to 70, then 70 is going to operate better than 50. If you have 90 degrees, it's going to operate better than the 70 degrees. Going from 50 to 70 would increase the flux by like 3 or more. And then the gap thickness. The gap means additional resistance to the flow of the material. Thermal resistance. So smaller gaps represent smaller thermal resistance and better performance. So decreasing the air or the water gap from 5 to 1 millimeter, just a drastic change in the thickness, is going to have a flux more than 2 times the original flux. Increasing the feed flow rate, increasing the flux. But you see here, the effect of the feed flow rate is less than the effect of the hot side temperature. Here we have tripled the flow rate of the hot side, yet only 30% improvement in the productivity occurs. The cold side also has an effect. The colder the temperature of the condensation, the bigger the temperature difference, the bigger the pressure difference, the more vapor that can occur. However, the cold side effects are less significant compared to the hot side effects. So hot side temperature, hot side flow rate, cold side flow rate, cold side temperatures are the ones that have less effect. Salinity of the feed is not a significant factor. So one of the good things about the membrane distillation technology is that it is tolerant. It can handle high salinity. And that's why in some of the applications, one of the projects, I was just talking with some of you that one of the projects that we have is use the high salinity, which is leaving a normal desalination technology, and take it as an input for a membrane distillation technology so that the membrane distillation technology can handle higher salinity. And then you have more recovery of sweet water out of the salty water that you would have. Challenges that are related to operating or designing or maintaining membrane distillation systems is they have a lower flux compared to the multi-stage flash. I have to repeat, the multi-stage flash has started in 1957, and over maybe 3 decades, it was the dominant desalination technology, and people have put a lot of effort for it to succeed. And then it succeeded for this period of time. So it took the MSF something like 3 decades to reach for a level of productivity which is too high, even more than that. I mean, the units that we have, Al-Khobar unit, for example, is used to produce something like 90,000 cubic meter per day for each unit. But the total productivity in Ras Al Khair, for example, has exceeded 1 million cubic meters per day. So we are talking about significant differences. And nothing can ever compete with the MSF in terms of the productivity, in terms of the numbers that it produces. We are talking about reliable units with very high plant factor. It does not go out of service because of maintenance of something, except for a very short period of time. And actually, practically speaking here, the plants do not do maintenance for the MSF plants once a year. They probably do it once every 2 years or so. Which means that we're talking about units that are at technology which is mature, it's well proven, and it operates, it produces very high fluxes. So far, the membrane distillation has low flux in comparison. It's not a large scale, so far, distillation system. There are ideas of making modules so that you, instead of bringing one desalination system, you bring something like 4 or 5 or 6 or 10 of a smaller size units. Maybe they don't have to be then placed in a central area, but they can be distributed. If you are talking about campuses, each campus can have a small number of them that would take care of the water needs. The membrane productivity can suffer from fouling. This is one of the issues, which is one of the problems that we are facing for thermal as well as for membrane distillation systems or membrane desalination systems in general. Fouling is one of the problems that affect the performance. If the membrane is wetted, it needs to be replaced. So the membrane here is dry. It's a hydrophobic membrane, and it should always maintain conditions of dryness. There's something that we call concentration polarization or temperature polarization. And these are one of the parameters that reduce the productivity of a desalination system in general. When we talk about it here, we can look at the membrane surface. Sorry. So there's a membrane surface, and the hot water is coming from here, which is the feed. And the permeate side is here. You need, as much as possible, a maximum amount of flow of the vapor to pass by the membrane. But This paper has to be pure. So this is on one side here. On the other side, you cannot increase the number of the pores. What you need to pass is basically the vapor. So there's some sort of a trade back or a trade-off between the membrane characteristics and the flow which is passing. But back again to the issue that I'm talking about. This is salty water in this side. And evaporation occurs close to the surface of the membrane. When the evaporation occurs, the vapor leaves across the membrane. It leaves behind a higher concentration of the salt. Eventually, with time, you'll find that there's a boundary layer forming on the surface here, with very high concentration of the salt on the surface, and the concentration drops as you are moving away from the surface, which is very much the same as the idea of the boundary layer. Very high concentration in one layer, and then the effects decrease as you are moving away from that layer. This is the concentration polarization. Is there a solution for it? Yeah, there are techniques for the concentration polarization. One of them is basically doing a backwash for the membranes. If it's an RO system, we just admit the water to be passing in the opposite direction so that it pushes the salt away from the surface. Can we do that with vapor? Yes, why not? It can be done in a way that you try somehow to clean the feed side. We're looking at applications of MD, desalination for human consumption. There's a breakthrough that has been done by a group from Spain last year that they come up with a membrane distillation system of Higor, much higher than the values that we could produce. And they were talking about the key for this issue is to have very effective energy recovery system. But we've seen that it can deal with different qualities of water. So dealing with water of high salinity is another benefit. Actually, it's only the HDH and the membrane distillation that are able to handle very high salinity compounds, like the compounds that are operating in the frac water industry. You are talking about oil industry, petrol recovery, and the oil to recover more oil from under the ground, you inject water in. Water passes through the rocks and it collects some of the minerals. The water comes out with very high salinity, extremely high. So it's well above 100,000 ppm. So HDH, membrane distillation are technologies that are able to handle this high salinity. Again, why? Remember, we do not have any metallic surfaces. It's all made of plastic, so we don't worry about what's going to happen like corrosion or something for the metals. We have done some work with membrane distillation units. So most of the work was started with experimental values, and in parallel we started making models for the membrane distillation systems. And we did a lot with direct contact membrane distillation, air gap membrane distillation, and lately water gap membrane distillation systems. So we built units. The good thing about the membrane distillation system is that you can buy a flat sheet of membrane, which is 15 by 15, but it should be hydrophobic membrane, not hydrophilic, not the membrane used for the RO system. So we used to buy sheets of the membranes, and we used to buy sheets of plexiglass or acrylic and build our own units ourselves here. We used to design and fabricate them in our workshop in building one, and then test them and operate them and modify and operate and modify and modify. And that's the way it goes. It's endless. Our first trial was basically with direct contact membrane distillation. We wanted to build a unit, build an experimental system, try to obtain values and benchmark what available data, and looking at the operating variables and the parameters that more affect the system performance. Remember that we're talking about 4 parameters in particular: the feed side temperature, the feed side flow rate, the cold side temperature, and the cold side flow rate. These are the 4 parameters, basically temperature and flow rate in the hot side and in the cold side. So we needed to see the effect of these parameters, which of them are more significant, so that if you are going to build a system, what is the parameter that you should worry about? Should I worry about increasing the flow rate more, or should I worry about the temperature more? High temperature or low temperature? Is it enough to use room water temperature for condensation of the vapor, or do I have to cool it down using a refrigeration system or a cooler? What's the problem with that? It would be better, yes, but it's energy consumption. If you are going to do cooling, then you need to apply maybe a vapor compression system, which is going to be significantly energy consumer. So we don't need that. You need to produce water as much as you can with the lowest energy input to the system that you have. Yeah, that takes care of like an introduction to the membrane distillation system. What we are going to do in the next class or two is basically we're going to start with a description of the experimental systems that we have developed here. Maybe I can put it in the form of sort of a history, and the units that we have developed. What we see here is our second generation of the membrane distillation systems that we have used in the university. So I'm going to cover that up to the ones that we are currently doing as we are speaking now. And then after that, we are going to move into the modeling. Maybe we'll pick up a model for direct contact membrane distillation and then go through it until the end. And after that, whoever is able to do that should be able to do the rest, like what would be the modifications associated with the air gap membrane distillations and the other ones. So I'm going to stop here, and in our next class, we are going to pursue the discussion of membrane distillation. Now, I have to tell you that I would expect you to submit the first homework by the end of next week, like a week from Wednesday. Now, I would assume that you have access to the ES, and you should be able to do this part of the work. And we need to think of a quiz. And I think that we can have a quiz next week, which would be related to, let's start with the solar still, so that, I mean, we can start with something like writing energy balance equation for different components. So that's something that we can begin with in a week from today. So next Sunday, inshallah, we're going to have that. So Sunday, we have quiz number 1, and Wednesday, we're going to have submission of the first homework. I need to prepare the second homework and release it, which is going to be related to the HDH system. Questions?